Alright, today is going to be the start of the actual math of what's going to be going on in here. Now, okay, yesterday I'm pretty sure I confused several of you guys on the methods of connection, so I'm going to talk about how that actually applies today. Alright, now let's say that we have a simple truss here. And I'm going to draw as simple as I can get. We'll just do a triangle. Here's this, this, and this. Okay, now most of the time what we are going to be working on, as a matter of fact, all the time what we're going to be working on in here is two-dimensional work. Right. When we are dealing with two-dimensional work, that means that we are only going to be dealing with the y direction and the x direction. Okay. Now, this truss itself, we always are going to assume that there are pins at either end of these members. The reason we do that is that with these pins, we know that those pins can supply a force vertically, they can supply a force horizontally, but they cannot cause any resistance to a rotation in either dimension. Because if you were to take this piece and try to swing it this way, the pin would not be able to stop it. If you were to take this piece and try to swing it either way, once again that pin would not be able to stop it. So due to that, you are able to assume a couple of things out of here. Now, the pin connections at the ends are important. But the other thing that's important for is determining, well, what exterior forces are going on it. So, what I'm going to say is that this structure is pinned to the ground here. So, because this structure is pinned to the ground right here, there are two forces that can be acting here. There's a force that can be acting straight up. There's a force that can be acting either forward or backward in this direction here. So, by noting that this right here is a pin connection, by noticing that that location right there is a pin connection, that tells us what forces I'm going to have to look for. Now, let's say that we have a roller over here. Now, a roller is not going to be able to supply a force in the x direction. Reason is, if you try to push it that way, guess what? It's going to roll that way. If you try to push it that way, it's going to roll that way. The only direction that this can supply a force is going to be straight up. So that is why these connection types are going to matter. Realistically, the ones that you're going to deal with more often than anything are going to be, number one, is going to be the pin connection. Anytime that you have a pin connection, there are going to be forces in the x and forces in the y. Okay? There is not going to be any moment contained within there. The second most common situation we're going to be dealing with is a roller connection. Now, this may weird you out a little bit to think about, but every bridge that you have ever driven across has at least one of these roller connections on it. The reason is, due to the thermal expansion and contraction of the bridge itself, to have the bridge permanently mounted to the piers that go down into the riverbed, go down near the train tracks, whatever it may be, due to that fact, the thing needs to roll on top. So it's, in essence, it is a flat deck sitting on top of roller skates that are sitting on top of a pier. Now, with a roller connection, you're either going to see a roller connection drawn as something that looks like a wheel or something that looks like a roller skate. And I know this is probably the worst roller skate you will have ever seen, but in general, those are the two situations that you're going to see. The key thing about rollers are always only going to have one force acting normal to whatever surface it is on. So in other words, if this is horizontal, so I'll draw the floor in here. If this is horizontal, then the normal force will be acting right there. Now, if, on the other hand, you have it acting on a sloped surface, the only direction that the force can be supplied will be normal to that surface. Now, the third most common one that we will deal with here is going to be cable connection. Now in a cable connection, there's always going to be one force in direction of the cable. Okay? Now, let me show you how this actually works. All right? What we're going to look at now is the math for the outside structure. Let's just call it the overall structure. All right? Now, let's say that we have that same truss from the last page. I'm just going to draw it a little bit bigger here. And I'm still going to have it the same exact method where this end is connected via pin, this end is connected via roller. Now, for general naming purposes, each connection, each joint is going to be named by a letter. So let's call this joint A, this joint B, and this joint C. By naming each individual point with a letter, that means that you can determine exactly what forces are acting on the pin, and through that you can determine what's going through the structure. But for simplicity's sake, I'm just going to talk about the overall external structure for right now. Now let's say that at point A we are applying a load of 100 newtons, a force going that direction. I want to know what external forces are acting at point C and point B due to that 100 Newton force acting right there. Now, the things that are important to know are the distances. Let's make this 1 meter long from C to A. Now also, notice the way that I'm drawing this. This is the standard notation for drawing. Make sure that you draw an arrow with solid arrow tips going from point to point so you know exactly what distance you're talking about. Secondly, let's say that C to B is also 1 meter in length. Once again, please notice the way that I'm drawing this up. This is typical convention. Okay. Now, like we said on the previous slide here, a pin is going to be able to supply 2 different forces. A roller is only going to be able to supply 1 force. What I'm going to do is I'm going to pick a direction. Doesn't matter whether I'm right or wrong. Okay? So, I'm going to say that there are 2 individual forces acting here. I'm going to change colors to make them stand out a little bit more. But, on point C, there's going to be a force from C in the Y direction. There's going to be a force from C in the X direction. There's going to be, due to a roller here, that means we're only going to have 1 force acting normal to the situation, which means that I am going to have a force at B in the Y. Okay? Now, these are the 3 things I want to know. I need to know how strong this pin has to be, and I need to know how strong this roller has to be. So what I need to do is start by defining positive direction. All right, define positive direction. Okay, now most people are going to consider to the right to be positive X and up to be positive Y. You can pick it however it best suits the situation and best suits your problem, but these are the typical conventions here. All right. The next thing that you want to do is set up equilibrium conditions in the X and Y directions. In some cases, you will be able to solve already. So I'm going to put in parentheses here, solve if possible. All right. Now, I'm going to put this in a different color to let it stand out. So, equilibrium conditions are sum of the forces in the x direction, and sum of the forces in the y direction. Sum of the forces in the x equal, sum of the forces in the y equal. So in the x direction, I've got 100 newtons acting in a positive direction. So that means this one is taken care of. In the x direction, I only have Fc in the x as well. This is going in the positive direction, plus Fc in the x. Now, because it is in equilibrium, that should tell you that this entire thing is not going to be accelerating, or the sum of the forces in the x direction is going to equal 0. Now, if you notice here, we've got 100 newtons plus the force of c in the x equals 0. We've got one equation with one unknown. We can solve for this right off the bat. All right, 100 newtons equals negative Fc in the x if I subtract Fc in the x from both sides, or subtract 100 newtons from both sides. Either way, the force due to c in the x direction is going to equal negative 100 newtons. Now, the negative sign here. All that negative sign means is I guessed wrong with my pick here. Instead of this being a force c in the x going in a positive direction, the force c in the x is instead going to be going in the negative direction. So that means that it is 100 newtons acting to the left instead of to the right. So this is the nice thing about noticing and locating what types of connections you have at the corners. By having a pin connection here and a roller connection here, I can tell that there is only one force that is going to be supplied in the x direction. The only location that that force can be supplied is right there. So 100 newtons to the left, 100 newtons to the right, I am in equilibrium in the x direction. The sum of the forces in the y is once again going to have to equal 0. But let's look at what we have here. All right, we've got Fc in the y, which is acting up, positive, plus Fb in the y, which is acting in the positive direction, and that's going to equal 0. So I may know very little here, but I do know that these two are going to be the same size but opposite direction. So in other words, force of c in the y is going to equal negative force b in the y. One of these is going to be positive, one of these is going to be negative, which means I picked the wrong direction for one of these two. Don't know which one yet. So right now, to find my positive and negative directions, I set up equilibrium conditions and solved for the force in the x direction. So I'm on the right track here. My next step, let's see if I can drag just this. Probably not. Of course not. All right, I'm going to move to the next page, but just place it right here on a dot or on a bulleted list immediately underneath it. All right. Next thing, you want to use moments to find any other unknowns. All right, so I'm going to change up colors again so that it is standing out. When we are doing moments, this is exactly the same as what we did with torques last year. So with these torques, remember, all you need to do is pick a point around which you're going to rotate. So what I'm going to do here is I'm going to pick this point right here, point C. Okay? So I want to find the sum of the moments about point C, and let's call this direction clockwise to be positive. So I am going to look at any forces that would cause a rotation about point C. Now, first of all, my force C in the y and my force C in the x. Notice that neither of those would be able to cause a torque. If I tried rotating about this point by pulling straight up or by pulling straight to the right, either one of those is going to cause the situation where it's not going to spin. It will cause it to translate in motion. It would cause it to move in a straight line, but it would not cause rotation. So what I need to do is I need to find any forces that are not acting directly through that point to determine exactly what's going on here. Okay? So, any forces that are not acting directly through this point that will cause rotation. Well, I've got two of those. I've got this one right here, and I've got this one right here. Now, just like torque from last year, what's going to matter is the force that's being applied and the distance it is away from the pivot point. And then you just tie in the normal sign convention as you're plugging in your numbers. So, let's look at what happens at point A. There's a force of 100 newtons at point A. Now that force would cause a rotation that would be in the positive nature. That would be a clockwise rotation about point C. It is 1 meter in distance away. So, I would have a positive 100 newtons, distance of 1 meter. Now let's look at what happens due to point B. At point B, I'm going to cause a rotation in this direction about this point. So it will be a negative direction of travel. The distance between those points is 1 meter, but the force is unknown. So it is going to be a negative rotation about that point. The force is an unknown. It is force of B in the y direction, but the distance is 1 meter. Now, just like we had torque in equilibrium last year, if this is in equilibrium, that means that there is no net travel, no acceleration around this point. So, 100 times 1 is 100 Newton meters, minus force B in the y times 1 is going to be 1 units of meters, equals 0. Well, let's add force B in the y to both sides. 100 Newton meters equals force B in the y times the unit of 1 meter. I divide both sides by 1 meter. Units cancel, units cancel. The force of B in the y is going to be 100 newtons. So, this tells me two things. Because the sign on this is positive, that tells me that my prediction of this being an upward pointing arrow was correct. That also tells me the magnitude. So I know direction and I know magnitude. That is going to be 100 newtons acting directly up. So, my force of B in the y is going to be 100 newtons. Now, here is the options remaining. I've got two different ways to finish this problem. Because I have already found what the force of B in the y was, and the only other unknown I have left is force C in the y. I've got two options. I can either, 1, use moments to find my last unknown, or 2, I can go through and determine what's going on with my original force equations. What I'm going to do is just prove to you that both of these ways will work. From the previous page, we had force of B in the y plus force of C in the y equals 0, or force of C in the y equals negative force B in the y. Now that I know the force B in the y is 100 newtons, force C in the y is going to be negative 100 newtons, which means it is going to be 100 newtons acting straight down. Okay, now to double check myself, I'm going to take and do another math problem involving the sum of the moments about point B. Now, when we do the live lesson next period, I will show you guys exactly why you want to pick which points in order to try to figure this out, make it a little bit easier on yourself. Equals. Well, let's look at the picture. Now, this time I am going to once again be finding moments, but this time it's going to be about this point. This force right here will not cause a moment about it. It will cause no torque because it's pushing through the pin. That would cause translational motion, not rotation. This one, however, well, look at it again. Pushing directly through that pin. My force C in the X is also going to cause me zero rotation. No rotation because it is pushing directly through that pin. There are going to be two possible forces that can cause rotation here. There is 1 and 2. Now, this force, even though it is acting at some angle, I'm looking at the perpendicular distance away. The perpendicular distance away is still 1 meter. The force is still 100 newtons. So let's look at that one first. So we've got 100 newtons times a distance of 1 meter perpendicular. The rotation direction would have been positive, so that is a plus. Now, this one, my force C in the Y is a distance of 1 meter away, and the direction of travel is, well, positive rotation about this. So, plus my force C in the Y times 1 meter. That is all going to equal 0. So, 100 times 1 is 100 Newton meters, plus, I'm just going to leave them separated this time, it really doesn't matter, equals 0. Subtract 100 Newton meters from both sides. My force C in the Y times 1 meter equals negative 100 Newton meters. Divide both sides by 1 meter. Units are going to cancel. My force C in the Y is going to equal negative 100 newtons. So there's more than one way to skin a cat. The nice thing is that by doing this in two different ways, you can check your work. Now, I am going to request that while we are doing these at the beginning stages, you show me at least 2 ways to solve for the last answer. Alright, now once you have reached the end, what you need to find is the forces on each pin, and you should define them, write them out separately. I had 3 different forces that I was looking for: force C in the X, force C in the Y, and force B in the Y. My force C in the X was 100 newtons, my force C in the Y was 100 newtons, and my force B in the Y was 100 newtons. Now, the last thing that I want you to show me is direction. Now, we knew that the force C in the Y is going to be downward. From the first page, force B in the Y is going to be upward, and force C in the X is going to be to the left. Now, once you have finished your answers, you know all of the unknowns that plagued us at the beginning. Box those, and we are spent. That would be the correct answer for this problem. I'll give you a couple of additional practice ones. We will work on them in class here and then see where we end up. Just relax for the remainder of this period until I can come back around and help you guys out. This should not be too difficult. The math on this is just going to be Algebra 1. So if you have any trouble, any problems, let me know and we will try to get them adjusted as quickly as we can. Thank you and good luck.